put a lot of thought into these and you know, be ready to ask questions or come in and ask questions, you know, or check your answers, that kind of thing. So with that said, what do you want to look at? Was this, by the way, I just want to comment on number one because this is such a common problem. So what'd you do here to start this one?
5 and bottom.
Yeah. Put a 5 in the bottom one for X, and then set it equal to the top one with a 5 put in for X, right? You put a 5 in for X in both of them, right? Because you have two equations. So again, this piecewise function, this is where we always see it, where they're talking about continuous. It's going to be continuous. We know a parabola is continuous. We know sine is continuous. The only place these could possibly not be continuous is where? At 5, when it breaks, right? When it switches from the parabola to the sine graph, you might get a break. But we don't want a break. We want the parabola to stop. We want the parabola to stop, and then we don't want the sine graph to start up here. We want the sine graph to start right there at that same spot, whatever it looks like, okay? So we want the y values to be equal, so that's why we put a 5 in for there, and that's going to be a certain y value, and we put a 5 in for there. And I don't know, what's sine of 5 pi halves? That'd be just 1, right? So 5b equals -20, and b equals -4, right? Okay. So just make sure you understand that concept. Okay, I'm sorry. What did you say? What number? Somebody said the number right about
18.
Okay, so remember, and the notation this packet uses, it uses dy dx a lot more than y prime, but remember, dy dx is just the same as y prime, right? So they're just saying find the derivative of this. So you got to do a product rule right there, right? So y prime is going to be, the derivative of x is 1, and then it's going to be ln x all squared left alone, plus x left alone, and then the derivative of that, you bring the 2 down in front, you leave the ln x inside, which to the first now, so bring the 2 down, ln x left alone to the first, times the derivative inside, which is 1 over x, right? That makes sense? And then right here, this x, and this x cancel, because you got this term here, and you got this term here. So we got ln x all squared plus 2 ln x. And then you look at your answers and they don't really match. Well, you could distribute, right, each of these, or you could do what here? Just factor out an ln x. If you factor out an ln x, that leaves you ln x plus 2. So, right here. Does that make sense? Was your derivative wrong?
Yeah, I missed it. I didn't think so.
See, and this is an example of one where I'm talking about, I would expect to see work on this, right? Number one, there's got to be some work, some things written down here. So I don't go through and grade. When I go through these packs, I don't grade every problem, but I pick out specific problems that I know we're going to, where I need, where there better be a certain amount of work in there. Yes?
13.
Okay. As soon as you read inflection point, what do you think of? Don't you think? Here's what I hope we would all think. Is that? Now, I would also hope we would think change of concavity, right? It's not this is only a possible inflection point, right? Remember on the chart? This is only a possible inflection point, but and smooth functions, nice things, whatever. That's typically the place to look. Okay, so it's possible that it's when the second derivative is undefined, like a sharp point kind of a situation, and you could have a change of concavity. But a really good place to check is when the second derivative is 0. So I need the second derivative. Now, first of all, k x to the negative 1 is how I want to think of that. Okay, so the derivative of this would be 4x, and the derivative of that is minus k x to the negative 2. Right, k is just a number, so it's just hanging out in front of that x. Okay, you wouldn't want to have, this is where, like I'm talking about, you don't want to think of a quotient rule or anything for that. K is just a number, so bring that x up and do that. Okay, that's the first derivative. So the second derivative would be 4, bring the negative 2 down and be plus 2k x to the negative 3. Now we want that to equal 0. Right? We want to check and see that the second derivative is 0. Now, it's possible that the second derivative is 0, but you don't get a change, like a flat spot kind of a situation with local max min. The second derivative could be 0, and you don't get a change of concavity. But it's multiple choice, and there is no inflection point is not an option or whatever, right? We're finding the value of k. So they're telling us there is an inflection point at negative 1. So what do we do? What do we do with this right here? Well, what do you mean solve it, though? Solve it for what? Yeah, we're going to solve it for k, but we've also got an x there. So what do we do with that x? Plug in negative 1. Yeah, I mean, and again, this is not like we haven't done problems like this when we find the inflection point. What we typically did is did the second derivative set equals 0, right? I mean, we just did kind of normal, basic inflection point, right? This is what I was talking about with the AP test. They ask him in a little different way. They love doing this, and this, of course, freaks us out until we start getting used to it. When they put this K in there, with an A, they put these, like number 1, they put a B in there, and we got to find those, and it just totally throws us off for a while, and it shouldn't. I mean, it just do the normal stuff you would do. Point of inflection, do the second derivative, set it equals 0, and then right here, now it changes. You'd say, well, normally we'd solve it. We got two things, but oh, wait, they did tell us that x has to be negative 1. So you put a negative 1. Now, anytime I'm working with negative powers, I told you didn't have to mess with that. You could leave it. But if you're going to have to do some work with it, then I think you want to go to positive power. So I would, if I was doing this, I would do that, right? Now we plug the negative 1 in. Well, negative 1 cubed is a negative 1. So 2k divided by negative 1 is going to be minus. That's going to turn that into a minus 2k, right? And now we just solve it. So 4 equals 2k, k equals 2. Hope I did that right. Okay. So k would equal 2. All right, what else? Equation of tan. Okay, as soon as we read that, I'm not going to read any further. As soon as I read that, what do I think? Y equals blank, x minus blank plus blank, right? Slope of 2 points. Slope of 2 points. Or, I'm sorry, 1 point. Two numbers, right? X and y. Well, look at that. They just gave me that. So there's 5, there's negative 12, right? So all I need is my slope, which is my y prime. So how do I do the derivative of that? 2x plus y prime, right? So we did the gateway test. We were working on, we talked about implicit differentiation. Sure enough, you're going to have it. Now, could you have solved that for y? That's a circle. We actually could have solved that for y, but then we'd had to know, are we talking about the top half of the circle or the bottom half of the circle? Which one are we on? No, that's why implicit differentiation is so much nicer. Matter of fact, I don't even need to solve for y prime right now, do I? What could I do right now? I can put my numbers in, right? I can just put my numbers in right now instead of worrying about solving for y prime. So I can put a 5 in here for x, and I can put a negative 12 in here for y. Right? I could just put them in right now. I don't have to. I could solve for y prime, which would be easy. I only have one of them, so I just move that over and divide, whatever. So I can do that too. Doesn't matter, but so I just plug in my x and my y from up here, and then divide, and I get 10/24, which is 5/12. So I got that. But as often happens on the multiple choice questions, your answer that you get doesn't look like their answer, so you look at what they've got and say, oh, okay, they want me to get it in that format. So now it's just a bunch of rearrangement. Now it's just a bunch of algebra. You know, maybe first thing you decide to do is distribute that. There's a lot of ways we could go here. There's a few shortcuts that you could do. Remember, when you multiply a fraction, when you take 5/12 times 5, it's like that. You just multiply across. I mean, this is the killer, as we do all this good calculus stuff here, and then all of a sudden we can't get the answer because we don't want to multiply two fractions, or something. That's, and then minus 12 like that. Okay, I don't know, what would be a thing to do right now? I would take everything by 12. Take everything by 12, clear the fractions. 12y equals 5x minus 25 minus 144. Don't forget, you got to multiply that last 12 there by 12. Right? You multiply everything by 12. And then that gets, so 12y equals 5x, that'd be minus 169. And I don't know, we're getting close. I see these all have that on one side, so maybe I'll add the 169 over to this side, so it's positive, and then subtract the 12y, so I have 5x minus 12y equals 169. 5x minus 12y. Right? I mean, so, again, typical kind of situation. You got some calculus to do, and on these no calculator ones, and they throw in a little bit of algebra, just make sure you can do some of that stuff too. Okay, but equation tangent line, point, slope, give you the point, find the slope by y prime. This time had to do implicit differentiation. What else? Three would be one that we could wait on. Well, we could talk about it. This is something we're going to do. Let's see. Will we get to it next week? Might not get to it. Might get to it late next week. But you can probably work it backwards a little bit. It says which expression gives a rate at which the slope line is changing. If you looked up the answer, what's the answer? It's this one, right? Which is actually secant squared, right? And then d theta dt is like theta prime, right? Right? So that's the answer, secant. So when you see something like that, secant squared theta times theta prime, what are you thinking of? Derivative of tangent is secant squared, first of all, right? And then when you see a theta prime tacked on the end, what does that make you think of? That implicit differentiation, right? Where you kick out the, right? You tack on the y prime, which is basically chain rule, right? Derivative of the inside, derivative of theta, because it's with respect to t. So somehow there must have been a tangent there, right? I mean, if we're kind of working in reverse, there must have been a tangent theta that we did the derivative of, right? And to end up with that. And so it says, which expression gives the rate? So rate, of course, is derivative, so we can see why we did a derivative, at which the slope is changing. So what we were trying to find is the derivative of slope, right? We were trying to find the derivative of slope. So we were like doing slope prime. Let's call it S. Let's call S the slope. Could call it M, I guess. Normally we do use M for slope. So let's say we're doing M. So that'd be like finding M prime. How fast is the slope changing? Would be like finding M prime. Well,
would slope just be like tangent that it's rise over?
Exactly. If you think about tangent, it says a line through the origin. So let's go back to this. So here's a line through the origin. Okay? And it's rotating around the origin. So it's going this way. So in such a way that the angle theta between the line and the positive x-axis, so this is the angle theta right here, right? Okay? So and this line is rotating. Well, that's just like trig, right? That's just trig. That's unit circle, right? Starts here on the positive x-axis, rotates up, right? So that's really all we're talking about. Well, if you look at this, what is the slope of this line? Well, it's rise over run. Well, what's y over x? tangent theta, right? So when we say the slope of this line is y over x, we're also saying the slope of this line is tangent theta, right? That's what the slope of that line is, okay? So we want to know how fast that slope is changing. We want to find m prime. Now we're finding it with respect to t, the time, right? So this is the new thing. This would be the thing we'll have to talk about, but we can talk about it right now. As time goes on, right, as time changes, 1 second, 2 seconds, 3 seconds, theta is changing, but also slope is changing, right? The slope of the line is changing and the angle is changing. So you have two different things, both changing with respect to time. It's kind of what we're going to, a little bit about what we're talking about today. And so it kind of fits in with what we're going to be doing today. So it's not like having a y equals x kind of equation, and we're doing the derivative of y with respect to x, right? We're not doing the derivative of how fast y is changing with respect to x. What we have is m and theta are both changing quantities with respect to time, t. So we want to know how fast this one's changing. We have to do our implicit differentiation. In other words, the derivative of tangent is secant squared theta times the derivative of the inside. Derivative of theta is theta prime. Now remember, the reason we don't, if I'm doing y equals x squared and I want to do y prime, dy dx, I just do 2x. I don't tack on an x prime. Why don't we tack on an x prime? Because it's just 1. Because x prime in this case would be dx over dx, right? Which is just 1. So we don't tack on an x prime, right? But in this case, m and theta are both changing with respect to t. We're doing the derivative with respect to t. So theta prime would be d theta dt, right? So it wouldn't be just 1, so we tack it on. So that's why that was the answer, okay? So we had to set up an equation for slope and then do the derivative of it. We'll get into that. That's called related rates. Related rates, because what we have in this situation is two things, the theta and the slope, that are both changing in a related way. Their rates are changing, but they're related to each other. As one's changing, the other is causing the other to change. So we call those related rates. That's how we work those. Okay? All right. So we have that yet to do. Kind of. Anything else? Yeah, a couple of you have talked about this, so this would be worth just doing real quick with everybody. But again, this says y prime equals x squared y squared. And they want to know, what's this mean? That's y double prime, right? That's y double prime. So that means a derivative of this. So you do the derivative of this, y double prime. You're going to have to do a product rule. So derivative of x squared is 2x. Leave the y squared alone. Plus x squared left alone, and then the derivative of y squared, which would be 2y prime, right? So you leave the x squared alone, you do the derivative of y squared is 2y prime, but I want to put the 2 up here. It just drives me nuts when people do x squared and then 2y prime. I mean, that just looks ridiculous. Why would the 2 be stuck in the middle of that? Now you can write it down the first time, but then move that 2 out in front of it, okay? Because too many times, here's what happens. People do this. People put a big dot there, and then they look at that and they don't know what to do with that. It looks weird, and they don't know it confuses you. That's not what it is. It's this. It's all one big glob of stuff, right? It just, the 2 needs to be out in front. Anyway, you look at your answer, y double prime, and you look over here, and it's not there. And what do you notice about these answers? None of them have a y prime in it. See, in this with implicit differentiation, anytime you're going to find the second derivative, this is going to happen to you. Because anytime you do the derivative again, you're going to do the derivative of some y's, and you're going to tack on a y prime. So anytime you do a y double prime, you're going to have a y prime in it. A lot of times we don't want to have a y prime in it. Well, but before you had y double prime, you had to have y prime, right? So when you have a y prime stuck in there, it's not a problem, because what is y prime? Right there. So you already have a y prime from your earlier work, so all you have to do is take that y prime and stick it in there when you go to y double prime. And the same thing would happen if we did y triple prime, right? If we did y triple prime, we would go blah, 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 a bunch of product rules, and we'd have some y primes in there, because every time we did a y, we'd have to tack on a y prime. So there'd be some y primes in there, but no problem. We just go in there and throw in an x squared y squared. Okay? All right, so we would get 2xy squared plus 2x squared y, and then in place of the y prime, we'd have x squared y squared, which is 2xy squared plus 2x to the fourth y to the third, which is that one right there. So we did that when we were doing implicit differentiation. I think we probably did maybe one of those. We talked about it, I think, one time. Maybe we did. I might be losing my mind. That's it.
And that's all you do.
All right. Anything else? Last chance. Okay. Well, hang on to those, and we will do some more another day. For now, let's get your notes out and see if you could find your Lion and Ranger worksheet. Lion and Ranger. Okay, and you probably need your notes out too, because we're gonna be writing down some stuff. All right, so when we were doing Lion and Ranger, now this part here you don't have to write down. I'm going to write it down up here based on what you guys have on your Lion and Ranger worksheets. But so we had the Lion was moving in this direction like this, right? The Lion was moving this way. I think the Ranger, if I remember, was moving the other way, right? The Ranger was moving like that. So this is what we call two-dimensional motion. Right, so we focused on one-dimensional motion. When we talk about position, velocity, acceleration, we've been talking about one-dimensional. So like Bismarck, we're about east and west. So just one direction, right? Horizontal movement or just up and down. We've talked about that. Positive to the right, negative to the left, okay? Two-dimensional now has both a horizontal and a vertical component. So like we're moving in a diagonal, okay? And so now we have to consider both the horizontal component and the vertical component, the x and the y. Okay, and so that led us into this idea of what's called parametric equation. So x prime would be how fast is x changing with respect to time, right? Well, how fast for the Lion? How fast was his x coordinate changing? How fast was he going this way? It says it in that first paragraph. How fast was he going horizontally? 0.5 miles every. This is a line. I want the line. 0.3. So the Lion was going 0.3 miles every minute. So x prime would be 0.3 miles per minute. That would be what we would call his horizontal velocity. That would be his horizontal velocity. Now, he's not going horizontally. He's going in a diagonal, right? He's going, what, north and east, right? But he's 0.3 miles further east every minute, right? And then what was his vertical? 0.1 miles every minute. He was 0.1 miles further north than he had been the minute before. So that would be his y prime. Okay, or dy dt, right? So here's a case. So this is a lot like that number 3 that we did, where we talked about is we have the Lion's moving in this diagonal direction. His x position is changing and his y position is changing. So they both have a rate. Say, so you have x prime and you have y prime, because it's with respect to t. And so that's where that dx dt and dy dt, that notation, can be helpful to help us think about it. Okay, but that's how phase change. Now, there's a couple other components here we got to talk about then, right? I mean, that's just, but nobody would you normally wouldn't talk like that. You'd be more interested in how far did he go in a minute, right? You wouldn't say, well, he was 0.3 farther east and 0.1 farther north. You don't talk like that. So what did we have to do to figure out how far he went every minute? What did we have to do? Well, rate is the distance divided by the time, but here's the key, is these distances are in 1 minute, right? So if we divide by 1, we're not doing it, right? But what did we have to find? Look at your work there. What did we have to find here? Well, yeah, we did find the slope because we were interested in... Well, okay, see, so here's the thing. Okay, so look what I got right here. Here's what gets confusing about this. Because all year so far, we've been talking about slope equals rate, right? Slope equals the speed, right? We do this, so we can take it, when we do the derivative, it's like the slope of the line, it's the rate of change. Okay, but now this is going to change here a little bit in these scenarios. Because what's the slope of this line? So let's do that first, since you mentioned slope. What's the slope of this line? 0.1 over 0.3, which is 1/3. Is that how fast he's going? That is not the speed that he's traveling. See, okay, so we got to back up here a minute. Now, when we talked about slope being the speed, that's because we had minutes down here on this axis, and we had feet, let's say, on this axis, and if we had something like this, and we wanted to know the slope right here, right, it was going to be feet over minutes, and that was going to be feet per minute, and that is speed, right? So the slope was the speed. But is that what we have in this picture? It's 0.1 miles north over 0.3 miles east. So we got it. So we got to understand that when we do slope, yes, it's a rate. It's a rate of change, but it isn't necessarily a speed, right? This is a rate. Yes, the line is traveling 1/3 mile north for every mile east, right? So that is a rate, but it's not a speed, right? We want miles per minute. We want miles. So I think Max, you said, or somebody said it, we got to take you said the distance divided by the time. So how do we get the distance? That's what I was getting at. How far does the lion actually go in that minute? Look at this picture and look at your work. I hope it's in there. The what? The what? Hypotenuse. Hypotenuse. You gotta find the hypotenuse. Right? This is where he's actually going. This is his actual route. This is his actual path right here. So we got to find that distance. So did you do, I think you did that, didn't you? You should have that somewhere. 0.1 squared plus 0.3 squared is what? You don't have that? 0.1 squared plus 0.3 squared and then the square root of that? That would be how far he goes, but that's in 1 minute. So it would also be how fast. What do you got? Right. Right. So he goes 0.316 miles in 1 minute. It's like if you go 60 miles, if you drive for an hour and you go 60 miles, is 60 your distance or is that your speed? You drive for an hour and you go 60 miles. Is that your distance or your speed? Isn't it both? Isn't it both? You went 60 miles, so that's your distance. How fast did you go to go 60 miles in 1 hour? 60 miles per hour. It's both. It's both. This is what he did in 1 minute, right? In 1 minute, he went 0.316 miles. So that's his distance, but it's also how fast he's going. He went 0.316 miles in a minute. So his speed is 0.316 miles per minute. Do you see how those are different? Those two are different. The slope is just his rise over run, right? The slope is more just the direction he was going diagonally. But the speed is how far he went in a certain amount of time. So they're different. They're different in this scenario. Okay? Now, how did we get that? Well, again, since this is both the distance and the rate, we could label this as x and label this as y, but we could also label this as x prime and label this as y prime, right? X prime is his horizontal speed, and y prime is his vertical speed. Now, how did we get those? Look what we just did. To get this one, we took y prime to get the slope. We took y prime divided by x prime. Notice how we just did that right here? We took y prime divided by x prime, right? Y prime divided by x prime. Now, think about that. That's dy dt divided by dx dt. Now, if you invert and multiply that, what do you get? What do you end up with? You end up with dy over dx. Oh, isn't that slope? Isn't that change in y over change in x, right? Or y is this way or x is this way. That is our slope. Oh, that makes sense. So we take y prime divided by x prime. That actually gives us dy over dx. Okay, now what about speed? What did we do to get that? We did the Pythagorean theorem. We did the square root of x prime squared plus y prime squared, didn't we? I'll put those in parentheses maybe. Okay? So we took x prime squared and we took y prime squared, and then we did the square root of that, and that gave us the speed along it. Two totally different things. Two totally different things, right? So we're ingrained to think that slope is speed. It's not. Slope is a rate. It's the rate of the y divided by the x. It's rise over run. But you got to look at the units. Most of the time our units have been speed, like feet per minute, right? But not in this case. Our slope is miles north divided by miles east. Okay? That's our slope. That's a rate. But it's not the speed rate, right? It's not how far he's going in a time unit. So it is a rate, but it's what we're going to call the slope of his path. It's the slope of the path, but it's not the speed on the path. Okay? So it's just like if we all ran a race, we could all run on the same path, right? We could all run on the same path, but we could all be running at different speeds, right? That's what we're talking about, right? So the 1/3 is the path that the line's on, and then this is the speed that he's on. Okay? All right. So, parametric equations. Here's what you need to put in your notes for parametric equations. All right? First of all, let's do this a little bit at a time. All right. So we got, first and foremost, parametric equations are when we have both an x equation and a y equation. We talked about this when we went over the line and Ranger a little bit. I know we didn't go over a ton, but we talked about the different equations you would get in that table at the bottom of the page. And we'll write those down here in a second. But think our most common use that we're going to do right now of parametric equations is going to be like with position and stuff, okay? But we're talking about two-dimensional motion, so we're talking about moving diagonally. Okay, we're going to do an interesting problem today where it's adamant. It's going to be we're going to have a graph that literally looks like this. Right? It's just like if you had a piece of paper. If you lay down a piece of paper and you just walked around, right? You just kind of zigzag or whatever, right? It's going to look like that. Okay. So at any time, at any given time, let's say the particle starts right here. Okay, so at any given time, he's got an x coordinate and a y coordinate. It's constantly changing, right? It's constantly changing. All right. So x would be his horizontal position, right? His horizontal location, his horizontal coordinate, and then y is the vertical coordinate. So, we've done position functions. We call it s or x if we're just on the x-axis, just moving back and forth. We have an x equation because the y would be 0, right? If we have a particle moving on the x-axis back and forth, then the y equation would just be 0. So you'd have y equals 0, which is the x-axis, and then you'd have x equals, and that would be its position. Okay, so those are the kind we've been doing. But now we're going to have some where we have equations for both. We have an x equation and a y equation. Okay, so if we do the derivative of each of those, so let's do this first. Okay, let's do number 1 here. Okay, so number 1 here then says, okay, x prime then, or dx dt, whatever, that's going to be the horizontal velocity. So now when we talk about velocity and position, we have to tack on this idea of horizontal or vertical, right? We got 2 dimensions going on. So x prime is going to be the horizontal velocity, how fast it's moving horizontally. Now remember, it's doing some of both. It's moving diagonally, so it's moving, and then y prime is the vertical velocity. Okay? Now, what could you tell me? Remember we were talking about going north of east and west of Bismarck. Okay? So watch this. So I'm traveling. I'm east of Bismarck, right? I'm in my car. Right? Here I go. East of Bismarck. Now, I'm going to turn around. Now, what do we say has to happen for you to turn around? You have to stop, right? The derivative has to equal 0. That was the velocity. That kind of thing. But realistically, in a car, are you really going to stop and then go backwards? What are you going to do? You're going to turn around. You're going to do like a U-turn or whatever, right? You'll get off the ramp or whatever. Let's say you're just on the road all by yourself. You're going to do a U-turn. So at some point, so I do this, and I do a U-turn, I do this. Now, did I ever stop? No, so we were saying before that so you're going east, before you can go west, you have to stop. Now, technically, that wasn't really correct, because if I'm going to do that, I'm going to go like this, and I'm going to do a U-turn, and I'm going to do this. I never really stopped. What did stop? My eastward velocity stopped, right? So in other words, at some point, so even though I turn around, when I do this, at some point when I get to the peak of this little U, right? When I do my U-turn, when I get to the peak of that, even though I'm still going, what direction am I going? I'm going north or south now at this point, right? And then as I turn, then I'm back this way. So same thing here. If I'm just kind of cruising around here, at some point, like when I get right up there, what stops? Or what is 0 at that point? Your vertical velocity would be 0, right? So you're still moving so this particle is wandering around, you're moving this whole time, right? It's moving this whole time. But when it gets up to here, its vertical velocity is going to be 0. What about when it gets right to there? Wouldn't there be a spot where its horizontal velocity is 0, right? It quits going, it's not moving horizontally. Just for an instant, right? It's moving just vertically, right? And its horizontal velocity would be 0, right? And what would it take for it to be completely stopped? What would have to happen for the particle to be completely stopped? Both of them would have to be 0. It can't be moving horizontally or vertically. Right? If both of them are 0, then the particle stops. But if horizontal velocity is 0, it just means he's not going horizontally anymore. He's just going up and down. Or if the vertical velocity is 0, he's just going horizontal, right? Okay. So, and then the slope of the path we already talked about over there, right? At some point, as he's moving along, this is the slope of the path, right, that he's on. But it isn't the speed that he's going, right? Because this is miles over here, this is miles east, and this is miles north right here, right? So our slope would be y's over x's. It's not going to be a time unit, right? Because there could be three of us on this path. And at this point, right here, we would all have the same slope, but we could all be moving different speeds, right? You could have different equations that would give you the same slope here, but there'd be different speeds. So the speed is different than the slope, okay, like we were just talking about a minute ago. So the slope is simply y prime divided by x prime. Y prime divided by x prime, because that gives me dy over dx. So isn't that interesting that you have a dy dt, which we think of as y prime, and you have dy dx, which we also think is a y prime. That's a problem with prime notation. It doesn't tell you what the input variable is. dy dt is different than dy dx. I mean, they're both y prime. This one's with respect to t, though, and this one's with respect to x. Okay, so important to understand it. Okay, so y prime divided by y. So if we have equations, we just take and put those equations on top of each other. Take the y prime equation, put the x prime equation, put them on top of each other, and if you want the slope at a certain time value, you put in that time value, and that's your slope. Okay? All right, and then the other part of this then is the speed. And again, we said the same, we already had that as well. We just talked about that. To get the speed of that particular particle, now you got to use this equation. X prime squared plus y prime squared, and then the square root of that. And that just comes from Pythagorean theorem. Because basically your horizontal, your vertical makes a triangle, but the actual path is diagonal. Okay? So the lion and the ranger were moving in a straight line, so we didn't have to have calculus to do that. All we needed was linear stuff. But if you're moving in a curve like this, now we've got to have calculus, right? Because we got to be able to do the slope at an instant, right? So we got to have derivatives to be able to do this, okay, on a curve like that. Okay, and then I just put the line. We already filmed those things. Don't worry about that. Okay. All right. So let's write down what those equations. I think we talked about this, but this should have been at the bottom of your table on the front page. So what was our equation? So this was the speed. This would have been the x prime, and this would have been the y prime on the lion. This would have been the x prime, and this would have been the y prime on the ranger. Okay. So what was our equation for the line? 0.3t, and that was it. Because it started at an x position. This is the position. These are the position functions, right, of the lion and the ranger. And then the y was 0.1t plus 51. Because remember, the lion started up at a y value of 51. So at time zero, so think about this now. What you get, remember what this x and y is, it's x and y coordinate. So at time zero, you put a 0 in there, you get 0 for x, and you put a 0 in for t here, you get 51. Well, that's where the lion was at time 0. That's where the lion started, at the coordinate 0, 51. And then 1 minute later, he would be 0.3, right? He'd be 0.3 this way, and he'd be 0.1 up. So 1 minute later, he'd be at 0.3 and at 51.1. Right? Because every minute he goes 0.3 this way and 0.1 this way, right? So that's how you get your x and y coordinates, is from this equation. And then what was the ranger? He was, that was 100 minus 0.5 t, and that's because he was going backwards. The ranger was going this way. So he started at 100 over here, but then he lost 0.5 every minute. So when you put a 0 in there, you get 100, and then his y was 0.6t, right? Plus 0, because he started at the point 100 comma 0. So when t is 0, at time 0, he was at 100 for the x, and he was at 0 for the y. And then 1 minute later, he'd be 100 minus 0.5, he's at 99.5, and then put a 1 in there, he'd be at 0.6. So 1 minute later, he came this way, 0.5, and this way, 0.6. So he's at 99.5, 0.6. So those are our parametric equations. We can put those into our calculator. We don't really have to. Well, you should be able to know how to do that. Matter of fact, let's do that right now. Let's go to your calculator. And okay, just for time's sake, I won't punish this one person who logged in already. Sorry, Max, way to go. Shouldn't have done it.
He's on page somebody else, right?
Okay, so let's remember, everybody, how to go into parametric. You go to menu, you go to graph entry, you go to parametric number 4. Okay, so let's just put in the Ranger right now, and so 100 minus 0.5 t, and then 0.6 t. Then we got to remember, we got to set this t. So we got to set the x and y window, the x and y minimax. We do that under window, but we got to set our t range here. Now t in this problem is minutes. So how many minutes do they travel? Well, wasn't it like 150 or something like that? Was that when they crossed, or no? It was before that, I think. Let's put like 180. Like 180, and the t step doesn't really matter. Now we got to set our x and y window so we can see it. So remember so the x was, where did the Ranger start? 100. So maybe go -10 to 110 maybe. And the y, the Lion was up at 51, but then he went higher. So let's go maybe -10 to, I don't know, 90. I'm just kind of guessing. But so we got to set our x and y. So there's the Ranger, right? So he started down here, and he's actually walking this direction. So if we traced, watch what would happen here now when Max traces on this. So type in a 0 and hit enter. Notice how it's the time now you're typing in. When you trace on a normal function, you're tracing on x. But now we're tracing on time. So at time 0, now hit your right arrow. And keep hitting your right arrow. It won't let you go right.
I hit my right arrow.
It should. Are you sure? Is yours tracing? Can you hit your right arrow? That's good. And now it's just bouncing back and forth.
Yeah, the values are changing.
Well, right, but why does it keep going back to?
That's that refresh.
Does yours just keep going,
Yeah.
Do what now? What?
Is that like refresh?
Yeah, that's not a refresh. That's just a. I think that just shows he's logged in. Well, anyway, if I just keep hitting different, you should be able to just trace. But I keep hitting different. Oh, that's weird. I'm not sure what's going on. When you right arrow, it actually goes left, right? Because you're right arrowing the time. You're 1 minute, 2 minutes, 3 minutes, 4 minutes. Okay, now let's hit tab and let's go in, and now let's put the Lion in there. So the Lion was 0.3 t for the x, and then 51 plus 0.1 t. And then change your t to 0 to whatever we had, 180 or something. And then there's a Lion. And notice it stops. Why does it stop? At 180 minutes, that's where it was. If he traces right now and types in a 180, that just tells you where it was. And then the neat thing you can do is if he types in 180, okay, that's where the Ranger was, and now hit your up or down arrow, and now type 180, and then that's where he was. So they're a long way away. And now, when did they actually? type in a 110. I think wasn't that when one of them got to the intersection point? That's where the Lion was at 110, and now hit your up arrow, yeah, and that's where the Ranger was at 110. So the Ranger gets there first, right? So that was the whole point of this. The Ranger got there first, and then he was gone. And then what time did the Lion get there? Like 150? 150. So the Lion got there at 150. Right, so the Lion got there later, so they did their paths didn't cross. But that's how you can so you only get parts of grass, right, as they go. Okay, one last thing I wanted to show you here, and then I'm going to give you this worksheet you're going to work on for your assignment. But this is the unit circle is a parametric equation, right? X equals cosine and Y equals sine, and it's the points on this circle. So Max, one more time, let's go to your calculator and let's delete out X2 and Y2. Let's just delete those out. That's good. Use clear. That's good. And then hit enter. Did you just hit clear?
Oh, yeah.
And then enter. Oh, yeah, clear and then enter. Go down to X2. Yeah, hit clear and then enter. There you go. And now tab and go to X1. And now put in cosine T. Of course, in trade class you call that theta, but T, and you have to do T here, and then sine T for Y. And then that tells you why. Notice the default for T is what? 0 to 6.28. Well, why is that 0 to 6.28? 2 pi, right? That's going to go one time around the unit circle. So hit enter. And now let's change our X, min, and max. Let's go to a square. Well, go to a standard. Go to 5, a standard window. And a standard window is square. Notice that the X's go negative 10 to 10. These go into 6.43 because it's wider than it's tall. So if you went negative 10 to 10 on both, it would not look like a circle. But that one looks like a circle. Now, if you cut both of those in half, it'd be a little bigger circle. So let's do that. Go to your window, just for the heck of it. Go to your window and change those to negative 5 to 5 and change this to just negative 3.2. Just so we don't have quite so much empty space. But anyway, that's your circle. And now if he traces, let's see if this thing will trace right this time. Trace and type in a 0. Now hit your right arrow. God, what that did is yours do.
It just flies off the circle.
The way it's supposed to, right? It goes like this, right? It goes around, which is what it should do. T is theta, right? And so as it goes around. God, I don't know.
Is this doing like one full turn?
Huh?
Is this doing like one full turn?
Well, yeah, it's just.
Go on there.
Yeah, but his T step is not. Now it's not doing anything.
0 and then 6.
Well, is that where you hitting the
It
left?
goes all the way around.
Were you hitting the left arrow there?
It is 0 and 6.
So, I don't know. That's just weird. Go to trace one more time. Let's try this. You guys go to trace. Go to trace step. Is your guys on automatic?
Yeah.
Yeah. See, that's what his is. So I don't think we went on anything else. I'm not sure what's going on. But if you put 1.57, type in 1.57, right? Which is pi halves. And so it's just the unit circle, right? Just the unit circle. So you've actually seen parametric equations before. All right. So I think that's about all I had. Okay, and so all right. So let's take this worksheet here. Now it says a square window. I guess it gives you that. It gives you that. Okay. So let's get started on this kind of together. So Atomac crawls along the XY plane. X and Y is given by this. And so this is now remember, put a time sign in between that T and that cosine T. So this is your parametric equation. Okay, they tell you what to use for your window. Okay. And so, but now we will actually do some calculating. And people always get all kind of freaked out about this. when we start this. But you just have these two equations here. One is x, one is y. Well, this is horizontal position. This is vertical position. If they ask you when is the horizontal velocity 0, just think about this for a second before you do any more. Just look up here. If I ask you when is the horizontal velocity equals 0, what would you do? Not the x equal to 0. I said the horizontal velocity. X prime. You would do the derivative of that, which would be a normal derivative, dx dt, derivative with respect to t, and need a product rule. Okay, I don't care if you let the calculator do it, but it's good practice for you to do it yourself. Do the horizontal velocity, set it equal to 0, and do a solve, right? Or if they want to say, what's the horizontal velocity when at time 1.5? You would just do x prime, plug 1.5 into it, right? That's all you're doing. Now, don't forget those other two equations. We had the slope equation, was y prime over x prime. And we had that speed equation, which was x prime squared plus y prime squared in the square root, right? But everything's based off of x prime and y prime, which are right here. You're given x and y, so all you got to do is a derivative of each of those. That's x prime, y prime. And then everything else is based off those. And it's just working with those. So it's not that difficult. All right, so let's look at the graph. So that's what you should be getting with your graph. Right? Well, in your parametrics.
So we make it like 12.4.
What's that? What are you talking about? 12?
The T's. How do you do it to 4 pi?
It says go 0 to 4 pi, and you're asking what?
So we make it 12.56.
Yeah, that'd be fine. 12 point. You can type in 4 pi. Actually, I think you can just type in 4 pi. But yeah, 12.56 close. And then I would just leave that t step at 0.13. That's fine. Okay. So the graph should kind of look like that. So basically, and then if you start tracing on it, basically what happens is that thing goes up here, and then it turns around. So it goes straight up here, turns around, and then it comes down. It's going to have you look at that little spot, so you can do a zoom. You can zoom in. What's that? I don't know why you just do it. Yeah, you're just going to have to be typing in numbers to do your trace, which is weird. I've never seen that happen. So I don't know why that would be good. Which is okay, it just can be kind of a pain when you're trying to find. But they're going to ask you questions like, when does it turn around? Like, look up here again, like what I was telling you. Remember we were talking about this. So what happens when it quits going up? Well, what is 0? Which is what? Y prime, right? When it quits going up, when it's hit its peak up and starts coming down, its y prime has to be 0, even though its x prime might still be something else. Okay? And when does it quit going to the right? Well, when its x prime is 0, right? When x prime is 0, when it quits going left or right. Okay? Because that's its horizontal velocity. What if x prime is positive? What's that tell you? Like right here. If this particle right here is moving this direction, what could you tell me about its x prime? Positive, because it's going right. What about its y prime? Positive, because it's going up. So, you get what I'm saying? So if it was over here, coming this way, its x prime and its y prime would both be negative, right? No. X prime would be positive, because it's going right. The y prime would be negative because it's going down, right? And so what you could do is, if we knew what time this was, at, whatever, at 7, you could plug a 7 into both the x prime and the y prime and see what you get, right? You get a positive x prime, you know it's going right. You get a negative x prime, you know it's going left, right? So you can tell it's going up and right or down and left or whatever, right? Ton of information just there in those equations about what's going on. Okay, go ahead and work on that.